Good evening, Calc 3 students. I hope you guys are well. Wanted to look at section 13.8 together. This is the second to last section that we're going to cover this semester, and it's the second to last section in your book. You're almost there. We're going to be talking about Stokes Theorem, and I want you to think of this as a higher dimensional version, a three-dimensional version of Green's theorem. Before we state the theorem, I want to look at just a basic setup with you. So we want to restrict ourselves to certain kinds of surfaces. So the surface that we want to look at is an orientable surface. We're going to go ahead and pick an orientation. So I said an oriented surface. And I want my surface to have a single, simple, closed, piecewise smooth boundary curve C. Now, that feels like a mouthful, but it actually isn't too bad. It's just saying that the boundary of your surface, the edge of your surface, needs to be a closed curve. And it's okay if there's a sharp point in it as long as it's piecewise smooth. So there's only finitely many sharp cusps on your curve. And then simple means it's not looping in itself like that. We want to avoid that situation. That's bad. And then a single curve. What do I mean by that? Well, at least for the purposes of our class, I want to avoid things like the cardboard tube inside your paper towels. That would actually have two different boundary curves, one there and one there. And there are ways to deal with that. But for our purposes, we're going to avoid that situation. We want to fill in one of those sizes and just have a boundary curve down here on one end. So those are the kind of surfaces that we want to look at. I'm trying to think of some examples. So you could take a sheet of paper, cut out an interesting shape with no holes in it, and then flex it. And that would be the kind of surface that we want. The boundary curve would just be the edge of your paper. Another shape that comes to mind is like a Pringle. Think of your Pringle chip. That would be an interesting surface, and the boundary curve would be the edge of the chip all the way around. Things like that. You could think about like a cup, and here the cup, the boundary curve would be the rim of the cup, and the surface would be everything else. So the point that I want you to see is this. When you have a surface, it's two-sided, and you've chosen an orientation, then you've chosen a normal vector for your surface. You've chosen which side the normal vectors go on. There's two choices. You've picked one of those. And then at that point, when you've chosen which side is up, i.e. where the normal vector goes, which side the normal vector goes for your surface, you've also induced a quote-unquote positive orientation of the boundary curve C. And the positive orientation of C is the orientation where when you walk around C, you're going in the counterclockwise direction with respect to the normal vector. So counterclockwise all depends on your orientation, right? And so here I've got my normal vector up, and as I go around that normal vector, I'm going counterclockwise around it. Your book describes it a little differently. I'll mention the way they talk about it. They say, imagine that you're walking along the curve, and you are standing, your up as you stand is the same direction as the normal vector. So my head is pointing in the direction of the normal vector. As I walk around the curve, I'm going in the positive direction if my left hand is reaching into the surface. So you keep the surface on your left the whole time around the curve. So however you want to think about it. And then I just wanted to show you, okay, if we flip the normal vector, so same surface here and here, I'm going to look at the other orientation. Well, when you orient your surface this way, now you've got to reverse the direction of C to have positive orientation. So that's the idea. Okay, so with that background in mind, we're ready to state Stokes theorem. So here we go. So same setup with our surface. I want an oriented surface, single, simple, closed, piecewise smooth boundary curve C. I'm going to go ahead and assume that C has positive orientation, meaning you can pick any orientation you want for S. All we ask is that you orient C in the positive sense with respect to S. All right, we're going to pick a vector field, big F, whose components have continuous partials on your surface S. Basically, we just want F to be relatively nice. Then the following is true. The surface integral of not F anymore, but the curl of F is a vector field, right? If F is a vector field, you can take its curl and you get a vector field. So we go ahead and put a vector S here. The surface integral of the vector field curl of F is equal to the line integral of the vector field F around C. And I want to go ahead and think about this maybe with a circle on it there, because I'm assuming C has positive orientation. Okay, so let's make a series of remarks. So first off, I wanted to give you just a little bit of intuition behind the theorem. We really can't go very deep at all, but I thought this might be helpful. So we're going to think about just a rectangular surface, about the simplest surface we could think of. And we'll go ahead and orient it just up that way. So my positive orientation on C looks like this. And I'm going to take that surface and I'm going to break it up into some smaller rectangles. This is very much like what we've done with back in Calc 1. We break up the x-axis and we first studied line integrals. Just the idea of breaking up what you're integrating over into smaller pieces. And what I want you to see is you've got your boundary curve C. I'll put C in pink around the outside, and it's oriented like this. When I break up my region, my surface, I get a new boundary curve, and each little square here has its own boundary curve, and they overlap. It's pretty clear that they overlap, right? So the key is this. I want the same orientation on each one of these little pieces of surfaces. And as I go around, watch what happens. As I go around this one, I do that. So I'm going this way. I'm going this way and then this way and this way. There we go. And as I go around this one, I'm going the opposite way. So watch with me again. This way, you're going that way. On this one, you're going that way. And so actually, this part of the surface, this part of the boundaries are going to cancel. You're going to get one negative, one positive of the same thing as you go around. Watch again. So this one, as I go around, I'm going this way. And the other one, as I go around, I'm going the opposite way. And those cancel. And so what happens is, on every one of the inside pieces here, they all fall out. They all cancel. And you're just left with the outer boundary curve C. That's fine and dandy. Where does the curl come from? Well, when we talked about curl of F, we said that it's telling you something about the rotation of the vector field around your point, your chosen point. And so you can actually, as you make these grid finer and finer and finer, you can sort of see curl appearing here, and everything else cancels out, and you're left with this C. And remember, when you think about the line integral of F along C, oh, my pencil just stopped working. There it is. We said that's the same thing as work. That's the work done by the vector field F in moving a particle along C. So this line integral is giving you, in some sense, rotation along the outer curve C. And it's saying, hey, if you take all the little pieces of rotation on the surface and you add them up, you'll just get the rotation around C. So that's just a few comments, very, very rough and not too specific, but gives you a little sense of what's happening there. Also wanted to tell you a little bit of interesting history. It turns out that Stokes' theorem was not discovered by Stokes at all. Sir George Stokes is who it's named after, and he was a very well-known, successful scientist. He did a lot of physics and mathematics, but he actually learned about this result in a letter written to him by Sir William Thomson. Now, you might have heard of Sir William Thomson under a different name. When he became Lord Kelvin was the name that he chose at some point. So he kind of changed his name to Lord Kelvin, and you have heard of him with the Kelvin scale potentially. Another fun fact, Stokes, he heard about this theorem in a letter from Lord Kelvin, and he wrote problems for this examination, this mathematical examination. And for whatever reason, he would put Stokes' theorem on there as a problem to prove. The problem was to prove Stokes' theorem. And nobody knows if any students were able to prove it or not, but that's kind of fun. Third remark that's pretty interesting. It turns out that if you have two different surfaces, S1 and S2, different surfaces, but with the same boundary curve, then the surface integral of the curl of F over one surface is the same as the surface integral of the curl of F over the other surface. Why is that true? Let's look at it. So here, I've got this surface in blue right here with this boundary curve, and I've taken the same boundary curve, but it's like, please imagine that this blue thing was like the little thin film when you're blowing bubbles, I dip this thing into the bubbles and I blow on it and I blow out this hot air balloon shape. So same boundary curve, very, very different surface. And yet both of them, the surface integral of the curl of f over the big surface collapses to the line integral of f around the boundary curve, and the surface integral of the curl of f over this little blue surface collapses down to the line integral of f along the boundary curve, and those are the same. So these surface integrals are the same over these very different surfaces, and so we'll see a little bit more of that as we go along. Well, let's break the video here, and then we'll do the next one. We'll look at an example